Thank you very much, everybody. As Joe has formally introduced me, I won't say too much about me. What I will say is the slides that I have today will probably take some in the region of 20-25 minutes, and it's really describing a workflow, describing a toolkit even that we've used for evaluating these hot sedimentary aquifers. The slide deck here today is something that I've put together in partnership with colleagues at various companies and organizations. So there's my WSP colleagues, there's colleagues at Geothermal Technologies out of Denver, and then also colleagues at Johns Hopkins University in Baltimore. So with that, I will move on. Okay, so just a couple of early comments around motivation. As we all know, the sustainability pressures that we face in the world today are really, focusing our intent in terms of looking at alternatives to fossil fuels, alternatives that have greener credentials. With that, we have lots of toolkit available for understanding the subsurface, for describing the subsurface, and part of the content that I'm going to show this afternoon is how can we innovate our geoscientific toolkits to actually sort of ride with this energy transition. One of those toolkits that has been around for a really long time is the Fracman software that we develop, author, we market it from WSP in the UK. It's a tool that I've been engaged with since the mid 2000s. It's been around long before that. So starting out in the late 1980s. It's started out in the nuclear waste industry. It's gone through conventional oil and gas. It's gone through mining. It's gone through infrastructure, and now it's very much sort of finding its place and being applied to real projects in the green energy space. So deep geothermal, carbon sequestration, and the like. Okay, so geothermal has to help us transition away from fossil fuels. It's a safe and sustainable approach. I would say most of the geothermal projects that we see tend to be the super hot. The super hot projects where there is lots of steam, there's a lot of heat there, there's also a lot of flow there, such that we can actually generate realistic power loads. So geothermal provides us with a reliable base load. It also allows us to be dispatchable in terms of how we use the energy that geothermal can provide. So it does provide us with a lot of benefits which other renewable energy sources like wind and solar cannot always provide us. So geothermal power generation, as I say, a lot of the fame that we see in projects around the globe seem to be these sort of super hot formations. So talking about the Forge project in the US, for example. So what I want to talk about today is that there are slightly different forms of geothermal where maybe we don't have exactly the same level of heat, but we have greater access to volumes of producible water or accessible water. And if we if we're able to maybe compromise on the heat but produce more accessible water, that allows us to still achieve the levels of power that we're actually wanting to get to. So that in turn means that we have to rely on both the porosity and the permeability of the host rock as much as the heat that exists in the subsurface. What these hot sedimentary aquifer type approaches mean is we can have long well life, we can have favorable economics, and it's reliable. Okay. But for those of us on the call that are involved in sort of geoscientific modeling, I think the workflow or the philosophy that I show here should be pretty familiar. So most of our geoscientific evaluations, nearly always rely on the initial development of a conceptual model description. So rocks come about, how did they maybe deform over millennia, conceptual descriptions of the subsurface such that we can then try to develop quantitative descriptions of those features. So it could be layering of the subsurface, it could be the different lithologies, the different rock types that we see in the subsurface within those layers. It could be, well, how do things like faulting and other sort of major geological structures appear, and how do they behave in the subsurface? So that conceptualization, as I said, leads to parameterization. So the hydraulic properties, so the porosity and permeability that I've mentioned already. It could be geomechanical properties, so it could be in situ stress conditions. It could be, well, how do those stress conditions interact with the natural fracturing, with the fault structures that we see. The one that's missing from there is the thermal properties, so the temperature profile, the thermal conductivities of the rocks, for example. So if we can integrate all of those things, we have the ability to develop a parameter model where all of those different features are integrated in the model description. We can then apply and test the model to actually help support any kind of decision making that we want to make. So today I'm going to sort of cover most of these things on this slide and actually demonstrate, well, how can we use that to inform the decision making for a geothermal project in the Denver Basin. Okay. The discrete fracture network method, as I said, it's been around a long time. It's probably considered or historically it's been considered quite a niche method. It's very much sort of rooted in multiple different industries, and you do find it across all of these industries being used commercially, being used academically to help improve our understanding of the subsurface. As I said, we can use these kinds of strategies to help us optimize design. So it could be optimizing a tunnel in the subsurface where we're looking at maybe groundwater inflow into the tunnel and maybe looking at, well, how do we remediate it? It could be enhanced oil recovery using CO2 injection. So how do we actually push CO2 gas through the fracture network? It could be, how do we connect with particular formations for producing hot water? And then the last one, it could be infrastructure, it could be slopes and tunnels. So it's quite a flexible approach. these are the different areas where it's it's found a strong track record, a strong level of innovation in understanding fractured rock masses, and I think that's what the DFN is really all about. It's about describing naturally fractured rock masses such that we can actually provide an improved modeling description of those rock masses, which in turn can then be used to improve our understanding and our development and design in those rock masses. Okay, innovation and resiliency. If we think about the key areas where the DFN method has evolved in terms of better describing the deep subsurface, the geological description. This is a key one. So one of the key areas that really springs to mind that is really quite novel, and as it happens, really important for describing flow in the subsurface is the intersection, the connectivity of natural fractures. So how different fractures intersect against one another, how they terminate, how they pass through. So it's actually about adding geological realism to the model, such that we're taking fewer shortcuts, fewer simplifications in terms of how we use these models to describe the subsurface. That in turn is supplemented by geomechanical descriptions. So whilst we're able to characterize intact rock properties in a laboratory, we cannot do those kinds of things for the rock mass. We have neither the means nor the capability to actually transfer large volumes of rock that have both intact components, have discontinuity components in the laboratory to actually characterize them as a rock mass. Fluid flow. So no longer are we in the days of simulating just single phase incompressible flow. Some of the tools out there today and we'll see one in action today, is it allows us to actually include complex elements of multiphysics. So it's not just about simulating the fluid flow, it's about simulating temperature, the hydraulics, and also the mechanical behavior of the subsurface. So it's a really complicated multiphysical description. And just the last point on this slide, models are getting bigger, models are getting more detailed, especially in the geothermal space, especially in the CCS space. So doing things where we can actually make use of data analytics and machine learning to actually achieve the best understanding of these models. Okay, the next section, I'm just going to talk a little bit about workflow and simulation, types of data that we typically rely on, and the process in which they're used. So the left column is very much the data that we look to load into our models. So it could be well data, so it could be logs, it could be outcrop data that maybe we use as an analog. It could also be seismic survey data. So there's lots of data types out there that we can really routinely use and actually help us build rational and realistic subsurface models. Visualizing that data is obviously key. Understanding how these different geological features exist in the subsurface. So visualization is really important. And then the characterization. So it could be different lithologies, it could be discontinuities, it could be well test data that we use to actually describe, well, what is the permeability and porosity in those subsurface elements. And through combining these first three items, we have a means of plugging, generally plugging pretty good data sets into an analysis phase. And as I mentioned a moment ago, that analysis phase can easily feed different technical areas, different technical disciplines, including deep geothermal. Okay, for geothermal, getting into a bit more specifics, the types of things that we're looking to characterize. So the geometrical properties. So it could be, for the case of a sedimentary aquifer, it could be, well, what is the aquifer thickness? How does the thickness of that aquifer change as you move from one position to another? I've said it was a hybrid approach. So it's not just about describing matrix properties. It's about describing the fracture network that also exists in that description. So the red text in each of these columns is the fracture components. The black text is the sort of more matrix-based components. So for hydraulics, matrix permeability, porosity, we also have the pore pressure state, mechanical properties, strength, stiffness, the in situ stress conditions would also be in there, and then the very last entry, the thermal properties, so temperature, thermal conductivity, specific heat. So these are the classes or groups of data that we typically require for describing the subsurface, especially for hot sedimentary aquifer analyses. There are other properties that I haven't listed here, but these are very much the main ones. Okay, the example that I want to talk about is from the Denver Basin in Colorado in the US. The photograph here is just a regular outcrop of the Lion sandstone. So the Lion sandstone has significant matrix porosity and permeability, but it also has significant secondary porosity and permeability provided by the fracture network. Geomechanically, it's quite weak. We would often sort of brand this as a type 3 fractured reservoir. So there is comparable contributions from both matrix and the fracture network. What's important about this location is it's a former shale gas patch. There are lots of wells that still exist. There is significant data sets available for this location. So we're very much in a data-rich environment here. Okay. Okay, so for this particular project, so I've mentioned there's geological, geomechanical, hydraulic or reservoir engineering components. This slide just gives a bit of a flavor. Well, what does that model actually look like? So the setup is based on a duplet of wells. We've got an open loop system, so meaning we're looking to inject fluid that migrates in the subsurface, hopefully heats up before hot fluid is then produced in a nearby offset well. That offset well, so the well spacing is for this formation, for these sets of conditions, we're looking at usually somewhere between 600 and 800 meters of separation. That separation is really key to understand. If we have the wells closer together, we can improve the likelihood of hydraulic connectivity between the two wells. So we can be more certain that fluid that we inject in one well is going to be produced hotter at the other well, but there are implications. Those implications could be, well, the colder fluid that we're injecting doesn't have enough time, doesn't have enough contact with the reservoir rocks to actually conduct some of the heat. So the fluid that we end up producing could be cooler than what we need. Obviously, if we space the wells too far apart, then actually we risk the chance of not having hydraulic connections between the two wells. So it's very important to actually locate and offset these wells properly. In terms of data, so we actually had lots of well data. The black lines on this sort of rainbow colored image are some well locations, and this is just where we've tried to almost interpolate porosity and permeability between different well locations. Obviously, with core data, we can actually constrain those porosity and permeability descriptions. With 3D seismic attributes, we can start being more predictive in terms of describing those rocks between the well locations. You can just about see the DFN model that's in this model. That DFN model is calibrated based on fracture data that exists on those wells. We have cumulative fracture intensity plots that can tell us about the fracture intensities. From the image log data, we can also determine, well, what are the orientations of the fractures. That in turn can also help inform our well planning. So we want to have geothermal wells that intersect as many conductive features as possible. So we want to have alignment with our well geometries, with our conductive fractures, such that we get the best contact levels in that geothermal reservoir. This gives a little bit more detail. So I've spoken about the wells and the well spacing. Injection and production, this is really key. So I mentioned in the opening slides that hot sedimentary aquifers tend to be a little bit cooler than some of the volcanic based geothermal systems. So as a way of compensating with slightly less heat, we look to be able to push greater volumes of water in that geothermal system. Some of the flow rates that we're looking to achieve, 50,000 barrels a day. So this is really rocking in terms of the actual flow through those wells. This is really high. The operation period, so longevity, having geothermal that demonstrate longevity is absolutely essential. For this project here, we were looking to achieve at least 25 years worth of operation. Okay, so the pictures on the right here just demonstrate really simply, well, what are the steps in that model making process. We have a basic structural description where we have seismic data. We saw on the previous slide, we had some well locations where we had log descriptions of porosity and permeability. We also have online descriptions, online resources for, well, what is the thermal gradient of the location? And we can use all of that information to take the well data and to build this DFN model of the subsurface. So these are the natural fractures that we observe on the image log. We basically can then combine them with the matrix descriptions that we see off of the wells, that we see off of the seismic coverage, to actually produce this hybrid description. So basically, we're embedding the contribution provided by the fractures in terms of porosity, permeability, and we're actually embedding that or combining that with the matrix description to give us this sort of more conventional grid-based reservoir model. Injecting 50,000 barrels a day, producing 50,000 barrels a day. We obviously know the temperature of the fluids that we're going to inject. What we're using the modeling for is to actually help us understand, well, what is the temperature of the fluids that we're producing? What is the longevity of that temperature in those produced fluids? These are a couple of snapshots from some of the simulations that we've done. So looking in plan view, so in each of these pictures, the blue colored well interval, as we see it here, is the injector well. The red colored interval that we see in each of these pictures, so the upper of the two wells, is the producer well. We basically simulate this we simulated it for 30 years of operation, and we can see the pressure profile. So we need to be conscious that the injection pressures do not cause us any issues in terms of containment. So things like caprock leakage, interaction with faults, all require us to understand, well, how does the reservoir pressure evolve during that injection and production process. Temperature profile, so we're injecting cooler fluids in this lower well. So basically that ellipse of cooler fluid will grow as we inject. What we want to do is make sure we're giving fluid enough time to heat up before it's actually produced at the producer well. So we can see how these things of pressure and temperature evolve as we operate. We can see after 12 or 13 years, we're basically thermally connecting these two wells, so we can actually see there's a direct connection there. We're not actually producing any of this orange material after about 13 years. So the orange colored material or fluid is the in situ starting state of the reservoir. So temperature and pressure in green. Oops. It's going so well. Hold on. Okay, so I spoke about injection and production being, quite high rates. I spoke about how the injection pressure, we need to keep that, we need to keep that under control such that the caprock remains intact. At the producer side, we also need to keep an eye on the pressures. So things like in this environment where we have a naturally weaker rock, so a sandstone, we need to keep control of the pressures, because that influences things like wellbore stability and sanding risks. The main charts here show, well, how do those pressures change as we change the relative positions of these two wells. So we can see if we have a closer spacing, if we have a closer spacing, we're not taking the fluid, sorry, if we have a closer spacing, we're taking the fluid away quicker, so the pressure actually doesn't build up. Similarly, if our wells are too far apart, we're going to be ramping up those fluid pressures much more quickly. Okay. Thermal drawdown in terms of well spacing, the model is able to directly help us in terms of optimal spacing. We can see, based on a 600-meter spacing and an 800-meter spacing, we're actually producing hot water of two different temperatures. Now, we may argue, well, actually, it's only, it's less than 10 degrees different. That can actually play quite a significant role, especially because your production rate may be constant. So, we need to be able to optimize the well spacing such that we get both the temperature and the achievable flow rates out of the system. What we can see from this is, if we reduce the well spacing, we're reducing the thermal recovery, but we're guaranteeing or we're improving the chances of actually that hydraulic connection. So there is very much a balancing act. In this type of environment where we're seeing, a significant matrix contribution to the flow, we can probably space these wells out a little bit more confidently than if it was just a standard fractured reservoir where there was, where the flow was totally controlled by the fracture network in the system. We have this concept of harvested reservoir volume. So this is almost like information that we use for a resources point of view. So how much of the subsurface is directly accessible by the geothermal system that we use, and we use a process called particle tracking. So what we're actually doing is releasing particles into the model, and they basically travel with the fluid flow as we operate this geothermal system. We do two forms of this particle tracking. We basically integrate it backwards and forwards in time. So what I mean by that is, at the injector, we release particles at the well, and we integrate through time such that we can predict, well, where does that fluid end up at a period of time later. For the producer, we still start the particles at the well location, but what we do is we then integrate backwards in time such we can say, well, where did that fluid start out? And what that allows us to do is understand, well, actually, how much at a given time are we producing natural reservoir waters, or are we producing water that has actually been injected and just heated up? So it allows us to understand, well, where is the water coming from within that aquifer? If we quantify those things, we can start to say, well, what is the permissible lifespan of this geothermal system? So when we start looking at time in the x-axis and the volume, the harvested volume that we saw on the previous slide, how that evolves, we can start saying, well, after so many weeks, months, or years, this is when things are going to start to change. I mentioned that we can also see, well, what are the contributions of the different fluids? So the red line here is actually fluid that's been injected, possibly injected multiple times. It's been produced, it's had the heat taken away, it's then been re-injected and then warmed up and then reproduced over and over again. So you can understand the contributions of those fluids. Okay, the next slide gives us quite a useful piece of information. At what timescale are geothermal resources really renewable? So if we have a geothermal operation, how long is the subsurface going to take to recover? For this case, we're probably looking at about a 300-year return period. So that's for the subsurface to naturally reacclimatize to its present day in situ conditions. So before we've actually started the production process. So 1 to 300 years, it's still a long time, but it is renewable. It's certainly not in the order of the magnitude of millions of years compared to fossil fuels, but it is also certainly longer than some of the sort of shallow ground source heat pumps. So they are renewable. They do not need geological time periods for regeneration. Okay, so with that, I've just got two slides left, and I'll open the floor up. So in summary, existing workflows that can be used for describing both the fracture network and the matrix description in the subsurface, those have been around a long time. They have been adapted and also integrated specifically for these types of geothermal problems. It's integrating, our core set of geological, geomechanical, and reservoir engineering or hydrogeology type skills. These techniques do support deep geothermal. It's not just the super hot environments, it's also hot sedimentary aquifers as well. These types of assessments do help us evaluate risk. They do help us design and optimize the production of geothermal systems. These techniques do also make use of oil industry standard technology in terms of data acquisition, but also in terms of the geographies around the globe where geothermal could actually be easily rolled out. My final slide, just a couple of acknowledgements. So my colleagues at GTI, my colleagues at Johns Hopkins University, and obviously my WSP colleagues, thanks to them. There are a few accompanying geothermal papers and publications that have been made over the past 2 years on this topic. And with that, I'll finish up here and open the floor to any questions. Thank you.